Hello, good to see you all again. Actually I just separate this second clip from the first one so the way you can enjoy watching it. Very short. Here we start with the types of soil water. Turns out that the water that you see or you can feel the moisture of the soil sample, that would be something that really different in terms of types of the soil water you have. At least we can categorize in three different soil water based on the energy involved. The first one is the gravitational water, or GW here. Basically, it's such a water that contains in the soil pore within a size range that equal or larger than 50 micrometer in terms of diameter of the pore itself. The second one is the capillary water, and this such a water basically contains in the pore size range between 2 micron up to below 50 micron of the pore size, right in the middle. And the last one is the hygroscopic water, or HW here, just the water that stay in the really tiny pore. Basically, the size of the pore itself is smaller than 2 micrometer. Now, if you can see from this figure, it might be helpful that because you have the soil particle right here, and you can see that this is water film. Start from here, and then you increase the thickness up to here. So if you think about this is like a channel in the soil system. So you can see that the gravitational water will just stay completely far away from the soil particle surface. So that means they actually didn't have anything to hang on. They just hang on each other water molecule itself. So that's why this type of water can be easily to drain out of the soil system, maybe after 2 or 3 days after the heavy rains, And it's if you think about that, when all the pore spaces occupied by water, you tend to have the saturated condition. So that means that you didn't have any empty pores at all, right? But after 2 or 3 days, this water that contain in really large pore size, like in this case, it's larger than 50 micrometer, it's going to be easy to drain out of the system. So that you can see that the more that you go far away from the soil particle, and that it's the gravity will take away of that mass of the of soil water. On the other hand, if you have water that attached to the soil particle, like in this case, you can see that hygroscopic water will be under the soil particle really much, because it stay probably really close to the soil particle surface, so it's kind of hold the water molecule really tight up here. But the capillary water is kind of in between, and this why this type of water is considered as available water. Not a whole part of this, but most of the proportion of this type of water we consider as the available water for plant as well. So you can see up here it's strong attraction and this weak attraction, and this is once the water get kind of like drain out of the gravitational water and you have capillary water left, plant kind of use up, and then maybe have some just a few amount left here, and then you will have some sort of a microorganism that can use up the water as well. And then you bring the soil sample back to the lab, and maybe let do some sort of air dry process, and then you will have just hygroscopic water left. And once you put this soil sample with just hygroscopic water into the oven, you actually dry up all the water to the air, so you have just dry sample left. Yeah, just think about that when you have an idea about soil water. Just think about this strong attraction here and weak attraction there, so it kind of helps to think about the soil water. All right, in terms of energy, because from now on we will not just discussing about the soil water in terms of amount of soil water, but when we like to talk about how they can pass into the soil system, we have to focus on soil water energy. So first of all, let me introduce you guys that we have two different kinds of energy. First one is the kinetic energy based on the velocity. So you can see that based on this equation, kinetic energy equal to m times v squared divided by 2. So that means if you have very fast velocity, you tend to have much more kinetic energy. Uh, Another one is the potential energy. It's such an elevation that causes energy change. So by definition, you will have potential energy equal to mass times gravitational acceleration, and then time h, which is the height. So basically here it's the elevation itself, the difference between high here and low there kind of make you a different potential energy. So in terms of soil water, think about how fast it is when it flows compared to the water in the river. It's such a relatively slow, right? So with that case, most of the time when we talk about energy in terms of soil water, it's such a really typical that we're gonna talk about the potential energy. So basically mgh, that's it in terms of soil water. So with that, I like to show you here that there is a concept about potential energy about water. Water tends to flow from where its potential is high to where its potential is low. From this figure, you can see that this is the side 1 here and side 2 here. Side 1 here has really high potential energy, but side 2 here has low potential energy, and that caused the water move from side 1 to side 2. That's the reason. For most of the case, of course, the elevation caused that uh, uh, water potential change, right? But in terms of water potential, they have some other components that can cause the potential get lower or higher as well. So don't be confused that all kind of position will can be just the answer right away. Not like, of course the water flow from the high spot to the lower spot, but it's not all any case it's gonna be like that. So you have to understand the components of the water potential at one point and compare to the interesting point as well. Otherwise you will miss the concept and then interpret differently. So the principle of the water flow and soil, we have maybe from the very simple equation to very complicated equation. I picked the really simple one here. The water flow, which is the lowercase q here, depends on, first of all, driving force, and the second one is the physical property in general, or you can say that hydraulic conductivity. So based on these two components, you can tell that how water can flow, fast or slow here. So basically it depends on the driving force, of course. Driving force is potential gradient here, and then the potential gradient, the difference between potential divided by the distance different, right? And times the hydraulic conductivity here. Well, actually I have to do something here as well. Actually we supposed to have the negative side here. I'm not gonna let you use this equation to calculate anyway, so just don't feel like it's gonna be really difficult or something. I put the let me show. I put the negative side here because that will help you to know what is the direction of water can flow. Again, one more time. So with this equation, you basically can tell that how fast a water can flow from one spot to another, and also the direction. Like you have A and B, how fast gonna be, and also direction from A to B or B to A is totally depend on the negative side here. So that's for really general for this equation. You probably know this equation. We got a name of that. This is the Darcy equation. Now let's take a look on the components of the water potential that you can have. Of course, for one soil you have total soil water potential, and its component will be a pressure potential, which is from higher pressure to lower pressure. You have metric potentials. Basically, this is somehow showing you how soil metrics or soil pore can absorb water to itself. So basically, from wetter surfaces of a solid phase in soil system to drier surfaces, or from larger pore to smaller pore, this is really important for metric potential, because we normally didn't have the soil system in saturation for that long. For most of the time, uh, um, you get gravitational effect, right? So most of the water will drain out, and all you have left is the water that contains in the small pore, and that causes a lot of the change in metric potential in one soil. Next is osmotic potential. This is totally depend on the salt solution in the soil system. But in the case where you have just normal soil, like in general, you don't interface with the value of the osmotic potential, basically, unless you have like saline soil or acidic soil, something like that. The last component is the gravitational potential. This is according to the gravity. So in any spot in the soil system, you will interface with the gravitational potential, of course. But the value itself, it totally depends on where you set up the reference base. So if you pick some location that above the reference base, this value will be positive. But if you pick some spot that below the reference base, the number will be negative. So it totally depends on your reference base you pick. Okay, one of the things that you have to know that some of these components cannot present at the same time, because the number is kind of continuous in the system, and that is the psi m and psi p. And this is condition that you're supposed to know, that pressure potential and metric potential is totally opposite component. They don't show up at the same time. So when the soil is wet or get all pore space occupied by water, basically you have saturation condition. So that means your pressure potential equal to 0, something like that. But once you have a lot more water above that saturation condition, your pressure potential will be above 0, get into the positive number in terms of pressure, of course. But when that happens, you have no longer what I'm trying to say is, when that happens, you don't have any value for the metric potential, because the soil is already right at the saturation point, and even above at the saturation point, so you won't see the metric potential. On the other hand, when the soil dries up, so after saturation you have psi p or psi m at the same point equal to 0. But when the soil kind of start drying up, so you have a metric potential play in role, so you get more negative number after that. So that's why psi p and psi m, they never show up at the same time. See, that is larger or equal to 0, where psi m is smaller or equal to 0. Osmotic potential for soil solution, we can assume that it's approaching 0, except in saline soil, like I said, where you can have a lot of ions in the soil solution. So in the mold system, some of the components can be negligible. Like in this case that we talk about upland soil, the water potential that we need to care about is gonna be metric potential and gravitational potential, because upland soil, it means the soil has really good drainage system. So that means you don't have a chance to get your soil saturated and conditioned that much. So that's why you have, most of the time, it will be metric potential. And you see that once you have metric potential, you don't see a pressure potential in the relationship. Whereas in terms of water locking system, like submerged soil, the water potential component will be consisting of pressure potential together with the gravitational potential. And this is because is above the saturation condition. For saline soil, of course, you have to add osmotic potential. And you can see that for any situation you will have gravitational potential involved always. So that's the reason, because of the gravitational effect is just everywhere, including soil system. Even you pick the different spot, you still interface with the gravity or gravitational effects anyway. So that's why you see them. You see the gravitational potential in any form of application. Next is some sort of function that I like to share, which is the soil water characteristic curve. This is really important because most of the time we talk about the amount of water, but I just introduced you guys with the energy of water. Now the relationship between the water content and the water energy or potential, in this case is we plot in terms of suction, so that why you get only the positive number here. The relationship between energy and water content, we call it water characteristic curve. And this type of characteristic is really helpful because it tells you that even like you have the soil that have the same amount of water, but then you can have different energy. So once you have different energy, it means that that same amount of water will release for plant to use different as well. So this is based on different type of soil texture, like you have sand, clay loam, and medium clay here, and you have peat here. You can see that once you have the metric potential go up here, that means you have more negative number, but we plot in terms of positive. So that means the soil get drier and drier. Start from this point, wet, completely wet, and getting drier. Let me show you here, and getting drier and drier, and really dry out here. And you can see the water content when you started, even you didn't do anything with the number here on the y-axis equals 0. You can see that you can get the water content, of course, because that is the saturation point, right? So you can see that sand has the lowest amount of water content, followed by clay loam and medium clay here, and peat, probably the most wonderful or powerful materials that can absorb a lot of water. And that's why at the beginning point, peat has the highest amount of water. But once you put into the situation where you can add more pressure to your sample, you can see that the water retention among different soil types here will give you different function. Like here you can see that at one spot here, from 0 to 1 suction here, you can see that all the soil sample can retain a lot of water, almost the same with the saturation point, right? But once you pass this point, or the characteristic curve start to change, like really different. In this case, you see peat just go down here and have just like maybe less than 0.4, and where it starts it's just like maybe 0.9 or something like that. So basically that this totally tells us that peat of course can absorb a lot of water, but for the water that plant can use, it just really just a little bit, just almost like maybe at some point is even lower than amount that you found in sand, something like that. So you can play around with this characteristic that give you the best or appropriate way to manage the soil water based on energy level, because you like to increase availability of soil water to plant based on energy level, so that way you can manage your soil water to be higher number, or that number is close to 0, something like that in term of suction. So that way you already give a higher potential of soil water into the agricultural system, and that why you can have the flow from whatever you give to the soil sample right through the plant roots right away, because we're still in the concept of high potential to low potential. So if you give the soil system with the high water potential, so that way that water can move from the spot you give it to the root system. So that way you can manage the soil water very effectively. Now, this is the term of available water capacity. I keep saying about availability of water so much. So here's the definition. The available water capacity, this tells you that basically the capacity, ability of soil can hold good water. Ability of soil can hold good water for plant to use almost right away. So by definition, you get the equation very simple here, that available water capacity equal to the upper limit where you can have the most availability of water, subtract with the lower limit where you can have the last amount of water that plant can use, which is the permanent wilting point. Beyond this, or right at the permanent wilting point, it means that your plant cannot take any more water, even you add a lot of water, because it just passed the point where it's completely wilt, completely being wilting. That's why we call permanent wilting point. So in terms of management, we like to keep the water in the agricultural system to right at field capacity, or this is the most upper limit for ability to subsidize for plant use. So that's why we like to get it back here. So normally when we do the irrigation, so we don't wait until the water getting close to the spot where you can see that the permanent wilting point, right? They kind of wait just a half of it and then refill water back up to the field capacity, and that's what we use in the reality in terms of irrigation. So you can see the upper limit here, field capacity, subtract with the lower limit, which is the permanent wilting point, and that is the capacity. We're not talking any about amount of that, but that capacity. Like you have what should I say? Like you have some sort of room that can store your stuff that really important, and the capacity is like maybe 3 by 3 by 3, or 3 by 3 by 3 cubic meter, something like that. The capacity, but the important stuff that you probably have just a half of that capacity. So in the next we'll tell you about the another let me show you, where is that? Okay, that's we show you the available water content in the next couple slides, of course, but keep in mind that this is totally the capacity itself. So the one of the things that you have to keep in mind, that this is really simple equation, and you just subtract use the field capacity and subtract with PWP, that's it. So make sure that you have both of them in the same unit, no matter what kind of unit you use. So keep in mind, otherwise it's not going to be equal like this. You will get some weird different numbers. Now this figure is showing you that once you have available water for plant growth, this is somehow it will look like in terms of soil pore system. Now let's take a look here, where you have here. This is totally wet saturation system, where you can see that all the gravitational water you can still see here in the system. So that means that all the large pores will be occupied by water, of course, and eventually this water will drain out, and then you will have just the capillary water left here, and this is where you start with the upper limit for available water. See that? And at the permanent wilting point, of course, it will be thinner in terms of water film here around soil particle, and we call that water is the hygroscopic water. So you can see the limit somewhere here. So when we talk about available water plant can use, it didn't mean that you have to soak your soil sample at all. It's just maybe moist, and it's even really hard for feel it by finger, or you're feeling that, oh, you're already right at the fill capacity. So it's just moist, that's it. So you can see how wonderful the plant can bring the soil water from that moist soil. Is really amazing. This table showing you different soil texture with different moisture variables in percentage here. First column air dry, and the second one is permanent wilting point, FC field capacity, and you subtract between FC and PWP, you get available water capacity. And this is the saturation point. First of all, I like you guys to look at the saturation point between coarse, medium, and fine texture of the soil. You can see that if all the pore spaces occupied by water, if you have coarse texture, this is something that you will get in terms of percentage of soil water. Medium texture, a lot more, and fine texture will be way a lot here, because all the little tiny pore can contain those water as well. So you can see that the whole capacity of all different size of pores can occupy or can allow water to be in there. Now take a look in terms of the fill capacity. The upper limit, you can see that you have probably the fine texture will give you the highest upper limit, followed by medium, okay, and the last one is the coarse texture, of course, because you have just you didn't have the numbers of the pore enough in terms of coarse texture, and most of them are really large, and that cannot contain a lot of the pore or pore water that's relevant to the availability for plant use as well. Now take a look of the permanent wilting point. You can see that the permanent wilting point, the highest one right at the fine texture. Remember, in fine texture, you also have the highest value for the fill capacity, but at the same time, you will have high value for permanent wilting point. At this point, it means that in terms of fine texture, like you have clay, you can't allow clay to dry most of the water. That's because you will get something that way below permanent wilting point. So you have to keep it wet or moist for most of the time in terms of the clay texture, because the permanent wilting point is very high value for that case, followed by medium texture and coarse texture. Now if we subtract between you start with the FC, subtract with the PWP, and you will get available water capacity. Now you can see something really interesting here, that for coarse sand, because it's the value of available water capacity come from the difference between FC and PWP, right? So yeah, it's predictable that coarse texture will give you the lowest number for available water capacity. But this is really amazing that for medium texture like loamy soil can give you a highest amount of available water content, because even the fill capacity is kind of a little bit lower than fine texture, but the permanent wilting point is way lower than the fine texture, and that's why it give you the big difference. And that's why if the story about loamy soil can give our probably the best condition for plant to grow, and one of the things is the available water content. And here is the figure that showing you one more time, where you have the volumetric water contents in y-axis and different type of soil texture in x-axis, start from sand, sandy loam, silt loam, clay loam, and clay. You can see that this is the fill capacity, this is saturation line, and this is fill capacity. Okay, and the last line here is the permanent wilting point. Now you can see that this is probably the biggest part where you can see the huge difference between FC and PWP down here, and that's caused by the silt loam or the very medium texture, like just up here, not clay and not sand, but something loam, silt loam or clay loam that can cause a lot of available water capacity. The next one that I actually just said something earlier, that available water content. Now we talk about content. Previously we talked about capacity. The water content here is available because we set something in the reference base, and that's the permanent melting point. So for any amount of water that above amount of water at permanent melting point will be considered as available water content. So it's pretty easy to do some calculation here to find out the available water content. So the WC here is stand for water content. Now take a look here, it will be much more easier. This is soil particle, of course, and this is three different types of soil water, where you have gravitational water, capillary water, and hygroscopic water that relevant to the situation where you have dry soil here. This is how you see water surrounding soil particle, which is the permanent melting point, and this is the FC or field capacity situation, and this is saturated condition. You can see that from the thickness of the water film, which is in blue color. It's really easy to follow here. Now take a look here, right in the middle, the capillary water kind of types of soil water. Now you can see that this is where we start. This is FC, because right at the FC of field capacity you have no gravitational water containing in the soil system anymore. It just drains out already. So this is where you start the field capacity, and the end point is right here, the PWP. Now if you talk about the capacity here, you see that the permanent melting point is not below here. In other words, even we talk about capillary water, but not all capillary water that fall into the permanent melting point. So be careful when you want to do the soil water management. You have to keep that in mind as well. Now start with the available water capacity here, where you start with FC and down here to PWP. The difference here of these two spots will give you available water capacity. Now take a look. That is the capacity, right? But when you go on the field and then you measure the water content right away, and this is the water content you get somewhere here. Now if you use that number subtract with the permanent melting point, that will give you available water content. The reason that I'm showing you the whole figure here, just like you guys to understand that the available water content and available water capacity is kind of different in terms of concept, but it's likely to see them equal to each other. And that's the case when you measure the soil water, and the value you get is just exactly at the field capacity, and that's where available water content is just equal to available water capacity. So keep in mind that that's the concept. Okay, the last section will be soil aeration. We talk something about solid phase, also about the soil color, and we just finished the density and everything about soil structure and also water. Now we move to also the very important part is the soil aeration. Soil aeration is changed according to the water content you will get. Like here, this is the whole picture of the soil component, where you have a solid phase, just a half of the whole volume, and the rest will be occupied by either air or water. So if you have a lot of water into the soil pore spaces, you will have low amount of the air, of course. So if you like to manage soil to get more air, you just make sure that you have a really good drainage for soil water. That's it. It's pretty straightforward. Here is the soil air component. You will see that you have nitrogen, oxygen, and carbon dioxide with different numbers comparing between soil air and atmosphere. You can see that number almost the same, but nitrogen in the soil is a little bit higher than in the atmosphere, where oxygen is a little bit lower in soil and carbon dioxide is way higher in soil compared to the atmosphere. Now you better know the reason why it's like that. Like plant root, you know that plant root is also need oxygen, right, to go on the respiration process to tear down the to what should I say, to digest sugar and change it into some other form, especially change it into carbon dioxide and water, and it's release ATP or energy uh, to use for some other activity. So that way, anytime that plant root have some sort of a respiration, the products will be carbon dioxide, and not just from the plant roots but from other activity of microbial activity or small animals also have a respiration process. So that why eventually the soil air will contain a lot of carbon dioxide compared with the atmosphere one. And that's the reason why the soils will be the place that release carbon dioxide to the atmosphere. Whereas you see that mm, the oxygen in the atmosphere is a little bit higher than oxygen in the soil, and that's the reason will give you the diffusion from the atmosphere and move into the soil air. Here the oxygen from the atmosphere to the soil system, carbon dioxide from the soil system to the atmosphere. This is somehow the circulation that occur that keep everything in balance and healthy. For air movement, it's totally depend on the mechanism. One of the things that really a major movement for air is the diffusion, and that caused by different concentration of the type of the air itself, from high to low concentration, of course. So that the reason why again carbon dioxide from the soil to the atmosphere and oxygen from atmosphere to the soil, and that keeps the airflow very well and have a really good for a plant to use. Now you have to make sure that you like to maintain such a air movement to go very well. So don't till when soil has a high water content, because that will destroy the soil structure and eventually you get compaction and air cannot flow very well to the soil system. Add some more organic matter or crop residue back to the soil system, so that way you can increase the total volume of the soil, have some sort of air a part of the volume in terms of soil system, and that way you can get the lower number of bulk density. And also grow some grasses and legumes plant as a cover crop, so that way it can keep all the soil structure very good, and release some sort of polysaccharide as a cementing agent to help the soil particle to form up soil aggregate and eventually have a lot of pores in terms of in terms of really good pore site distribution, and that have water and air flow very well in the soil system, and that keep the soil system really good for plant and for us as well. Again, this is the overall picture that I like to show you, that after you knowing the soil texture, which is the limitation or potential of the soil itself, and you know something that you can manage in terms of soil structure, you actually know the pathway or pore site distribution of the soil itself, where you can store or have them transport very well in terms of mass and energy in the soil system, and relevant to the surroundings of the soil system, where you can have water and air, heat or nutrients that circulate in the whole system, and that give you really good condition for plant to grow. Alright, that's all for the section that I am responsible for. Hopefully you guys can understand what's going on here, and if you have any question, I'm more than welcome to answer that, either via the class, Google Classroom, or you can send me an email, and anything that I can help, I will. So hope you guys enjoy watching this, and get give me back feedback and comments as well, so I can improve these materials as well. Otherwise, thank you so much for watching, and hope you see you guys sometime. Yep, bye bye.